Okay, so first I want to thank Shota for the nice introduction and the general review of all the previous literature results, and which requires much more background knowledge and the physical insight of what I have and what I need to present my work. But in my work, I'm going to be more precise and to fill in some of the details that Shota didn't have time to cover. And but the basic setup is the same as what Shota mentioned. So I think that saves also some of my time to tell what subject we are studying. So the setup is that we start with the QFT in Euclidean ADS space with d plus 1 dimension. And to be precise, we're going to use the round metric. So the boundary of the ADS will live in a circle sphere, roughly speaking. And let me start with our precise conjecture, which relates the correlation function of the boundary correlators and the S matrix in flat space. So our conjecture goes like this. These K1, K2 are the momentum with the S matrix. And this is equal to the flat space limit with some normalization factor, and then the correlation function on the boundary. And to be precise, we here only consider scalar operators with conformal dimension delta. In general, it's delta 1 to delta n, and here as well. Now, all these n's are the coordinates that parameterize a boundary point on the sphere. So let's say we take a boundary point P, and this is basically parameterized by this n or n tilde, depending on incoming or outgoing. While for the bulk point, we will denote it by x, which is parameterized by the rho coordinate in round sphere, round metric, and again this n mu. Let me put a subscript here. Okay, so the conjecture is not finished yet because there's a very important part which is continued to the so-called S matrix configuration. So first, let's take a look at what our conjecture wants to say. What this wants to say is that we take the correlation function of boundary operators, which is defined by taking the correlation function in the bulk, and we push the bulk points to the boundary. That's our correlation function. And then we want to analytically continue all the boundary points to some complexified value, by which we mean S matrix configuration. And the precise meaning of S matrix configuration will be clear in the talk, which is a very key point of our work. And then we say we take this correlation function, we analytically continue up to some normalization factor, then we take the flat space limit. After all this, we get the S matrix in d plus 1 dimensional space. So just to emphasize a little bit, as Shota already mentioned, so here we have a d-dimensional correlation function, while here we get the S matrix in d plus 1 dimensional space. Okay, so the rest of the talk, let me give a very brief outline. So we'll first give an heuristic argument of our formula. It's like how and why we came up with this formula, while it looks like so. And then we will explain what do we mean precisely by this S-matrix configuration. And in the last, I will give a bunch of examples of how this works and also what are the consequences of our conjecture. So let me start with the heuristic argument. So very pictorially, we know the correlation function on the boundary is calculated by a Witten diagram. Let me specify to a 4-point function, which is not very important in this moment. So we know the Witten diagram lives in ADS space. And naively, we want to ask, what if we take the ADS curvature to infinity? So it seems like we are going back to the flat space. So one would naively say, well, I would take the Witten diagram, which is scattering amplitude, roughly speaking, in ADS d plus 1. We take the flat space limit. It seems like we just get the Feynman diagram. Or it's like we are trying to erase this circle. So how precisely does this mean? Let us take a look at the building blocks of the Witten diagram. Let me first write down the results, and I'll explain how we got them. So the flat space limit of bulk to bulk propagator between point x1, x2 is just d plus 1k while the flat space limit of a bulk boundary propagator with a boundary point P and a bulk point X will become with some normalization factor and e to the delta mu nu x nu. So here the m is just the mass, which is, as Schroter have written down, we have this relation in the flat space limit. The conformal dimension just becomes the mass of the corresponding asymptotic state times the ADS curvature. So that's the result, and let me explain how we get it, okay? So for us, it turns out that this second case is more interesting. So I'll present the argument for the second case, for the bulk boundary propagator, while it's very similar to obtaining the first one. But already you see here, it's like, this looks like a Feynman propagator, right? It's in the Fission space. So let me be more precise. So we take the bulk boundary propagator. And with some normalization prefactor and e to the minus mr log 1 minus rho over r and x mu and p nu delta mu nu. And then we take the flat space limit. This just gives 1 over square root z e to the m and p mu delta mu nu rho and x nu. Now if I identify this bit as a new variable, which I will call x, this can be written down as basically what we have here. Okay, So that's very simple. And, but take a look at our results, right? For the bulk-to-bulk propagator, it's just a Feynman diagram. And for the bulk-to-boundary propagator, it looks very similar to the external lag, but not quite, because we are missing the I factor here. So now the question is, how can we really obtain the building blocks of Feynman diagram from these two bulk-to-bulk propagator and bulk-to-boundary propagator? So the question is, how do we get where the plus and minus sign correspond to incoming and outgoing states in the flat space. And we will use the mostly positive metric. But it's not very important here. So we started from the Euclidean signature. And we know from this eta mu nu precisely here, we know we want to go to the Lorentzian signature. And there's a standard step in doing this, which is the Wick rotation, and it's very simple. So let me separate x by its time-like component and spatial component, and the same for y. So it's easier for me to write down the Wick rotation. So the first step is to obtain the external legs is to use the Wick rotation. Which is just x0 is equal to y0. And sorry, there's an I factor here, of course. And that's standard and fixed. But of course, this is not enough. Because if we also Wick rotate our n here, we will not recover this I factor. So we need to do something else for the boundary positions, let's say. But since the first step is already fixed, so we just know whatever the boundary point needs to do to obtain our external legs. And it turns out to be like this. So again, I also will separate the spatial and the spatial, not really spatial, but it will be clear, the spatial and the time-like components of our n vector. Where again, this minus plus sign and the plus minus sign here corresponding to whether we want to continue to ingoing state or outgoing states. So it's like in or out. So now these two equations are precisely what we mean by asymmetric configuration. So there are two comments in order. So first of all, we take our boundary point, and then we analytically continue it to some complex values. And then they are identified with the momentum in flat space. So this is very non-trivial. And let me write it down. So this is only a heuristic argument. So we don't mean by any means we are being precise. It's just a way to first start off and to have an idea of how to write down the conjecture. So this is our non-rigorous way of deriving the conjecture. Let me add one more question mark here. So this is not proved yet. It's just a conjecture. So I want to say a complexified boundary points are identified through our equation star, are identified with a flat space momentum. So there's an immediate result from this comments, because if we now specify two 4-point functions, we know the boundary points. From them, we can calculate the cross ratios. While on the other side of this map, from flat space momentum, we can calculate the minus variables. So this just means we have a map between cross ratios in CFT, in conformal theory. Again, by this star equation with Mendelssohn invariance. So now if we, again, go back to our main conjecture, I hope it's more or less clear what do we mean by every bits here. We take the boundary correlation function. We analytically continue to the asymmetric configuration, as is written down here. And then up to some normalization factor, we take the flat space. And then we conjecture it to give us the asymmetrics in flat space. Are there any questions at the moment? OK, so far so good. This basically finished the first two parts, which is very quick. And then, so as the ON, yes.
So if now I take this map and I compute the Mendelssohn invariance, and I also compute the cross ratios on the CFT, I reproduce the map that Schotter was.
Yes, yes. And I will show this precisely in my talk, like in a few minutes. OK, as I confessed and as I made it clear, our argument is just heuristic. And now it's time to check, right, what we are saying is correct or not, or to what sense or to what extent is it correct. So let me give some very simple examples to test our conjecture. So now let's go to examples. The first one is just the simplest we can think of, which is the 2-point function with boundary points P1 and P2. OK, let me not write the equal sign here. So up to some normalization factor. This just only depends on the distance between the 2 points. And now if we want to write it in our sphere metric, the round metric, we need to do a change of coordinates. And we also need to do some up to some wild scaling. This is towards SD. This becomes 1/2 to the delta. Which by some simple algebra is equal to sine theta 1/2/2 to the power of 2 delta. And then we do this analytic continuation. This just gives, let me write it down. Two times square root of pi delta over cosh. So here I explicitly restore the factor I need because that's the correct factor for us to give the result what we want, but it's not very important for the main idea. So, but let's have a look at this function. It's very simple. The cosh over theta of theta 1, 2 is basically a bump where the horizontal line is just theta 1, 2 over 2. And then this bump is, the amplitude of this bump, or the magnitude of this bump, is characterized by 2 times square root of pi delta. Now we can ask, what if we take r to infinity, which is essentially the same for delta going to infinity, right? It's like the peak goes higher and higher, while the support goes to smaller and smaller, which looks like a delta function. And indeed, it's the delta function, as what we would expect in the flat space. So as r goes to infinity, we get the delta function. And it's very easy to check because for this relation to hold, we can just integral on both sides, and you can see they give the same result. And also we know in the flat space limit, the magnitude goes to infinity, so it's precisely the delta function. And similarly, we can do something more. If we consider a contact diagram with 4 external points meeting in a center point, what would this get? Well, from our intuition, we know this will just become the Feynman diagram in flat space, and which is just the momentum conserving delta function. And indeed, so this can also be checked. This is just the momentum conserving delta function. So these are some nice evidences of that our conjecture works, at least to some extent. And so far so good, but there are other more complex examples. But before showing you that, let me first go to the kinematics, as Zhao was curious about the map between cross ratios and Mendelssohn invariants. So in order to talk about Mendelssohn invariance and cross ratios in the conventional sense or in the normal sense, we want to specify 2 4-point functions only. Are there any questions so far? So we focus on 4-point function. And to start with, let me define Mendelssohn S and T in this way. Where I remind you this N1 and N2 are just the position points on the sphere. So this is not immediately the Mendelssohn variables we are familiar with. This is just some function if you want, but I call it S. Well, similar for T. So I think it's a little bit different from Schroter's convention, but basically I'm swapping minus MT and minus MU because I'm trying to use the CFT convention because 2 going to 3 is the T-channel OP limit. But also this I can, okay, this are in the Euclidean region where we started off. And if we try to use this map to analytically continue, basically this becomes, not precisely, this becomes the minus m variables in flat space. And for T, I can also write down it as a function of scattering angle and minus ms. So from now on, I will specify 2 equal mass cases because it's simpler and easier to manipulate. So with this map, we can try to connect cross ratios and minus invariants. Basically, we start from, let's say, U is equal to P1 minus P2 square, P3 minus P4 square, over P1 minus P3 square, and P2 minus P4 square. But these terms are calculated here, right? So if we, again, go to the round metric, the P1 minus P2 square is just 1 minus cos theta 1, 2, where the theta 1, 2 parameterize the difference between P1 and P2. So what I have is 1 minus cos theta 1, 2. To 4. Okay. Now, I want to remind you that if we want to talk about minus m variables at all, we need to impose the momentum conserving condition. What this means from our equation here, we're trying to say that theta 3, 4 square, cos theta 3, 4 is just equal to cos theta 1, 2, and the same for these two. So basically what I get is squared without these two. And then if we look at S and T here, and we can calculate it, right? For example, S is just equal to 2m squared 1 plus cos theta 1, 2. Sorry, yes, it's 1 minus. Okay, and same for T. And then you see immediately the relation between U and V and S and T are just related by this cos theta 1, 2, and 1, 3. So then we come with this relation between U is equal to 4m squared minus S over S plus T squared. And V is equal to but we also know there are relations between U and V and rho bar and Z and Z bar. So we can generally work out the relations between, let's say, ST and rho bar, which is what Schroter had written down before. So in particular, we want to specify, because here there's a square, and we want to know what is square root of u, right? Because there are two choices. And our choice is that because we started off from the Euclidean region, and our choice that in the Euclidean region, u and v are in their principal sheet, which means, let me write it here. Square root of u is equal to 4m squared minus s over s plus t. Because you see in Euclidean region, s and t, and also minus some u are all between 0 and 4. So this gives us that the square root of u is positive in the Euclidean region. And from this, we can also work out the general relations between rho and st and rho bar of s and t, which is kind of the reverse or inverse of Schroter written down, which was, let me just rewrite it here. Okay, so I don't want to write down the general expression here because it's very complicated, but there is a very simple cases that I would like to present. Is that if we use this formula for t, and we fix the scattering angle theta, and then things become very simple. Then the relation is rho s, where I put a S matrix superscript here, and I'll explain later. As a function of s and scattering angle is simply square root of s minus 2 over square root of s plus 2 e to the I theta minus 2 pi. When s is greater than 4m squared, and also theta is between minus pi to pi. So now why do I want to insist there's minus 2 pi? Because this is just 1. The reason is that this minus 2 pi is precisely the same or corresponding to this asymmetric superscript here, because as we will see in a moment, it's only when rho is continued to the second sheet, then the phase of rho becomes the scattering angle, modulo 2 pi.
Do you mean that rho bar would be just the same times e to the minus I theta without phase rotation?
Yes, after I draw the plot, I think it's clear. So I have given the prescription of how to analytically continue from Euclidean region to the S matrix configuration. And let me show you precisely how we do this. So let us start. So we would like to start from the plane of S, -m S and -m T. I think it's easier, one of the most easy way to visualize. So this is S, and this is -m T. And here is 4, where I set m squared equal 1. I think it shouldn't be too confusing. And this triangle here is, as I mentioned, is where both -m S and T and U are between 0 and 4. So this triangle corresponds to what we call the Euclidean region. While here is the familiar region where we would call S physical. And here is U tilde to be distinguished from the cross ratio U. I will use U tilde for -m U, physical. And here is just the T physical. Now, as I said, we want to fix the scattering angle, theta. So what we do is we start from some point in the Euclidean region, and then we fix theta. We analytically continue to some point in the S-physical region, and then we go on. So here there's a dashed line, and what I mean here is that if we look at the complex plane of S minus ms, where this is 4, we are really going into the complex plane of S. So from here to here, the dashed line means we are leaving the real plane, while the solid line means we stay in the real plane. So what does this give for rho and rho bar? It's, there's a very nice picture. So if we draw the unit disk where rho and rho bar lives, and we have a branch cut from 0 to -1. So the starting point is the Euclidean region, where rho and rho bar are just complex conjugate of each other. So I will denote by this very thin line here. And then we analytically continue using the first step. So rho will go into the second sheet across the branch cut. Note that we have fixed the angle. So at this point and this point, the scattering angle is the same. So it's actually telling us that if we draw a line through the center of the circle, the endpoint must lie on the circle as well. And the same goes for rho bar, but the difference is that rho bar stays in the principal sheet. So somewhere here. There's also a straight line through them. And here again, they are complex conjugate of each other, but up to the phase, which is this -2 pi. So this is first step, and the second step is even easier because now we have this formula, right? We know rho is parameterized by modulus and phase theta. And since we know we fix theta, so rho just go with fixed theta, where here correspond to s equal infinity, s going to infinity. Because you see, if we take s to infinity here, this is just 1, which is the boundary of the unit disk. So this particular map is very nice because it tells us that the scattering angle theta can be interpreted as the argument or the phase of rho, to be precise, +2 pi, because it has to be in the second sheet. So there are other interesting limits, kinematic limits we can think of. So I want to mention 2 very briefly. The first one is the double light cone limit, where Shota has already mentioned, is that if we go to this point where s equals 4m squared, s equals 4 and t equals 4, and u tilde is -4. As I mentioned, I have the different convention as Jota, so I swapped t and u. I hope it's not too confusing. So this is the double light cone limit in ST plane. And what it looks like in the rho plane is what we are more familiar with. It's just rho going to 0, which is equivalent to z going to 0. And here is rho bar. Again, they start with being complex conjugate of each other. And then rho bar just go to 1. This is the double light cone limit. There's another interesting one I want to mention is the Reggie limit. So the Reggie limit is, I think, it's originally defined in ST plane. So what we mean by Reggie limit is that we want to keep minus mt fixed and positive. So we first go to some point here where t is fixed and positive, and then we take s to infinity. Again, this dashed line means we are leaving the real line of s for the moment, and then we will land back at this point. And what this looks like in the row and row bar plane is just that, again, they start from being complex conjugate of each other. And then, again, row just go into the second sheet, while row stays in the principal sheet. And then they land on the the Lorentzian region, where they are real and independent of each other. And then, again, since we send s to infinity, we know row and row bar will go towards the boundary of the unit disk. So that's the end of the Reggie limit. The endpoint of Reggie limit looks like so. Any questions?
Can you realize this configuration? Let's say that the S physical, the first one,
Yes.
on the Lorentzian cylinder?
I'm not sure because what we have is we start from Euclidean signature, we go to Lorentzian, but then we go a step further, we go to this asymmetric configuration. So to be honest, I'm not sure how to visualize this asymmetric configuration as a geometric configuration. But maybe Elliot has something nice to say about this. Okay, just want to mention one last point, is that I'm already mentioned that there are some more complicated examples that we have encountered, which is not as nice as the delta functions. I'll just briefly sketch the result and then conclude. Basically, we want to say that if we take a scalar exchange Witten diagram, and we want to divide by the contact diagram, because we want to get rid of the momentum conserving delta function, because in the flat space limit, the conserving delta function is just singular, which is hard to deal with. So we want to divide it out, and then we take the flat space limit. This will just give us, let me use a B to label the mass of the exchanged particle here, S minus mb squared. When S minus 4m squared is greater than 4m squared for any ST being complex. So if you remember what Schott had presented, he has this relation that S should be greater than 8m squared. So here we have a more general result because we are dealing with some simpler and more explicit example. But basically, what Schott has is only applicable to the physical region, while here we are more general. For this explicit diagram, we can just explore the whole complex S-plane, which is partially crossing symmetric. But of course, within this disk in the complex S-plane, we don't know, because that in this region, if we continue to this region, we take the flat space limit, we just get infinity. So that's the region we don't know about. And yeah, I think that's all the results I want to present, and that's my talk. Thank you very much. Yes?
Is there a way to, for example, prevent linear vertices?
Sorry, to
Is
prevent?
there a way to reject the fact that, for example, the interaction that you consider do not have like linear vertices?
Sorry, can you say again? Sorry.
Cubic vertices.
Yes. You mean we can?
Yeah, is there a way to prevent to built in this derivation the fact that you cannot have like trilinear couplings and only like quartic couplings? Don't know.
I'm not sure I understand. So I think we can, in a practical level, what we are doing, so our prescription starts from momentum space, precision space. But in practical, we calculating in the, for this particular example, we are using Melling space. So of course, you can do a cubic or quartic vertex. It's just, if we really want to get a result, we need to first get the amplitude or the correlation function of this particular Witten diagram. So you can just hand me a Witten diagram with a cubic or quartic vertex. And I need to know the Melling amplitude first.
Yeah, I'm talking about like if you don't have this this pulse in the amplitude, maybe you can extend the analyticity region.
Yeah, that's true.
Okay. So.
I mean, maybe a related comment. The correlator is supposed to be a nice analytic function. The amplitude has poles, and it was always a bit confusing how you could get these poles directly from the correlator if you had such a prescription. And here we see sort of that the pole is now surrounded by some kind of blob where the flat space limit just is infinity. But outside the blob, you get a nice function 1 over s minus mb squared.
And if you look at more diagrams, is it always this blob? Well, if it's a quartic diagram, it works everywhere, right? That's, I guess, your statement.
Yes, if for the contact diagram, it works everywhere. But because also Shorter has found similar results for the bubble diagram. It's also, again,
What is the region for the bubble diagram?
what is the
region of convergence?
for that, it's s greater than 8 or smaller than 0, greater than 8, because for bubble diagram, we can only go to the physical region, not the entire complex S-plane.
You mean it's too complicated to analyze?
Yes, we haven't done it yet.
So the moment you take delta to infinity and r to infinity in a way that delta over r is fixed, so is it possible to try to take delta and r to infinity, but in a way that delta over r goes to 0, maybe very slowly, much slower than they go to infinity individually? Is there a hope that it will still make sense, the formula? Question to all of you. Yeah, no, I understand what the physical outcome. I was just wondering if the formula is generalizable in this way or not.
You're asking if you can write an expression like that, but that also takes into account massless particles?
Sort of, yeah.
Come to my talk later, and I'll explain.
Okay, now that we are all motivated to come back after lunch for Elliot's talk, let's just thank Xian again and go for lunch.
Thank you.